Good morning. I am Akash and I'll be giving this presentation on behalf of my team. The objective of this project is to implement a ship simulator and also to implement a predictive model in order to estimate the path trajectory of the vessel. To begin with, I'll go over the literature that we have made use of, followed by the prototyping that we have done on Jupyter Notebook, and finally I'll go over the demonstration of the final web application that we have implemented. So the first paper that we made use of is the flatness-based MPC for underactuated surface vessels in confined areas. In particular, we have made use of equation 1a to 7d, and the ship dynamics or the nonlinear differential equation is mentioned in 7a, which pretty much describes the behavior of the ship. In order to make use of this differential equation, we use the RK4 integrator in our implementation, which I'll go over in a bit. In the notebook, you can find this implementation here, as you can see. Following that, we make use of this paper, which is the model-based fault diagnostic algorithms for robotic systems. And in here, the fourth section is what actually is the focus of our implementation, which is algorithms based on adaptive extended common filter. Here from equation 18 all the way to 31, we have a one-to-one mapping in terms of the code that we have written. And equation 19 and 20 require us to compute a Jacobian matrix, which we have done using the SymPy library. Here it gives out a lambda function, which is a representation of the Jacobian calculation, which I pretty much copy over to my original notebook here. And thereafter make use of it in the computation. The RK4 implementation is here at the top, and as required for our project, or rather as required by the adaptive extended common filter, in real life the way it works is you have sensors, and those sensors sample data from the real world, and the adaptive extended common filter uses that data in order to predict what the actual state of the system might be like. In this case, obviously, we don't have sensors. We just made use of the RK4 integrator to simulate sensor data and then fed that data to the adaptive extended common filter, which gave us the estimates that we plot in our final presentation. Moving on to the actual simulator. The simulator is a web application built using React. The interesting bit that we explored in this is to make use of the Pyodide project, which is a WASM port of all the Python libraries and the Python runtime. You can run the simulator on your browser by going to this link or going to my repository where you have this link hosted where you can just click on this and it should work. Since this is a no server based implementation, everything runs on your browser pretty much. So to begin with, I have a reasonably set default, which you can of course change if you want. And theta1, theta2, which I forgot to mention, is the fault parameter. U1, U2, and U1, U2 being the actuator forces, basically. So U1 being the forward and U2 being the rudder, and theta1, theta2 being the fault parameters. Both these set of vectors have to be predefined for a path to be computed, obviously. You can, of course, like change these values to see other scenarios, experiment with them if you want, or report any bugs if you see. Following that, you can open the chart panel. So as you can see, the RK4 calculations are displayed here as sensor data. In real life, this would be rather sparse because sensors usually don't collect data at this frequency. And the adaptive extended common filter is designed to work with that constraint in mind. But since we are using RK4, we can go down all the way to 60 hertz. So why not? Then we have the estimated global parameters and local parameters. So before I go into that, let me quickly describe what they are. If you go to the first paper, here's a diagram. So based on the global axis, you have X, Y, and Psi. And based on the ship's local coordinate system, you have U, V, and R. So that basically makes up the global and local parameter set. So the adaptive extended common filter predicts the estimated global parameters based on the sensor data, and it's pretty accurate. So it pretty much overlaps the data. Like there is very small error, I would say, as you would expect from something in this case, since we have a 60 hertz sensor data with us, the adaptive extended common filter doesn't really have a problem estimating this. Similarly, we have the estimated local parameters and the estimated fault parameters based on what we had set here. Close this panel. Feel free to start the simulator. The ship starts moving. You have a free camera that you can move around, or you can click on this to follow the ship. You can also use a top-down view, which is also nice. And if you want to see the path that the ship is supposed to trace, you can click on this and it draws a path for you just to show how the ship will be moving around at sea. We also have basically a visualization of the prediction that the adaptive extended common filter does. You can click this. The pink dotted line is the prediction or the predicted path, and the ghost yellow ship is basically an offset ship. Basically, ideally it should overlap the ship, but in order to visualize it properly, we just offset it by 100 frames. So that's why it is ahead of the original ship. Feel free to play around. So I'll just zoom out a bit, or I can just use the follow camera. And it's again like a 200 seconds long simulation, so it's going to take some time to finish. So you can just pause it if you want, play it again, or just go to the start. So feel free to experiment with different force parameters. Of course, I can just maybe change things a bit. Maybe I can give it a wildly massive forward force and maybe compute it for a shorter period of time. Why not? Maybe 60 and compute. And the new computed path is ready. Of course, it changes in real time, so you can change different, or rather try out different parameters as you would see fit. And yeah, so that's it. Thank you for listening, and thanks.